Hello and welcome everyone, my name is Nick. In this video I'm gonna talk about VxLAN technology. This is an essential piece of every modern data center, hence it's vital to understand how it works. So let's start with our agenda for today. At first I will give you a quick overview of VxLAN, then I will discuss motivation factors to use it, and after that I will show you an example of basic workflow. Then I'm gonna go through data plane and control plane details and explain how routing works with VxLAN. So let's get started. VxLAN stands for Virtual Extensible LAN. It is a tunneling technology which allows bridging over routed network. It is very similar to MPLS, Layer 3 VPN. And you can also draw parallels with other tunneling technologies, for example, DMVPN. The most popular application for VxLAN is data center networking, including intra-DC forwarding as well as inter-DC forwarding. VxLAN leverages UDP encapsulation, and here you can see VxLAN header. So on the right side you can see original Ethernet frame, which we are going to forward leveraging VxLAN. So this original frame is encapsulated inside VxLAN, VxLAN is encapsulated inside UDP, UDP is encapsulated inside IP, and finally IP is encapsulated inside Ethernet. So apparently it is just a regular IP traffic. But UDP encapsulation is a very important point here, and we will get back to it in just a moment. Next we have that VxLAN offers 24-bit address space, and this is a really big number. You can raise 2 to the power of 24 and see it for yourself. And finally, VxLAN offers ECMP, which stands for Equal Cost Multipathing. Basically, it means that you can utilize all physical links inside your fabric, which is very important from capital expenditures or CapEx standpoint, because typically fabric links nowadays are 10 or 40 or 100 gig Ethernet. And as you may know, these guys are not cheap. You don't want to invest money into something that just stands still and doesn't forward any traffic until failure happens. And key factor which enables ECMP is UDP encapsulation, so these guys are really tied together. The easiest and most reliable way to make ECMP work nowadays is to utilize 5-tuple load balancing. So what is 5-tuple? 5-tuple is a combination of source and destination IP plus protocol plus source and destination port. VxLAN networks load balance traffic via changing UDP source port number for different flows at VTEP level. We will explore it in more detail later, but remember that this thing is really important. Now let's talk about motivation for moving to VxLAN. So here I have 3 bullets: extend broadcast domains, increase number of broadcast domains, and maximize link utilization. Let's go through them using diagram and some drawing. So what do we typically have inside our data centers? We have our endpoints, our servers, which are typically located inside racks. So here is our rack number 1, and at the top of the rack we have our top of rack switch, and below it we have bare metal servers, hypervisors with virtual machines or VMs, Docker hosts which host containers, Kubernetes nodes, etc, etc, etc. And we connect our endpoints to our top of rack switch. And as long as we are talking about just a single rack, everything is good. All our endpoints are interconnected and they can talk to each other. But what happens if we need to expand, if we need to add more servers? We would add rack number 2, and we will use basically the same approach. We will connect servers inside rack number 2 to top of rack switch. Same story is happening here. And here we face our first issue. How do we interconnect our racks? Because obviously we need some connectivity between, I don't know, between, for example, bare metal server here and Docker host here. The easiest way to establish that connectivity is to directly connect our top of rack switches. But this approach isn't good because it isn't scalable. So in real life, we will place intermediate switches like Nexus 7K or Nexus 9K. These guys are big physical boxes which typically contain multiple line cards, multiple supervisors, multiple power supplies. They are highly available, they are redundant, etc, etc, etc. And we interconnect our racks via top of rack switches and via intermediate switch, which in our case is Nexus 7K or Nexus 9K. But we don't want high availability only inside this single box. We also want another level of high availability, and that is why we place one more intermediate switch in order to deal with cases if first one is goes down completely. And here we will face our second problem, and to demonstrate it, let me show you the same diagram, but in more logical view. So here we have our top of rack switch number 1, top of rack switch number 2 for rack number 2, and here we have our spines. Spines in our case are those intermediate switches, Nexus 7K 1 and Nexus 7K 2. Nexus 7K 2. So with legacy technologies like spanning tree, we will have the following situation. At first, we will also interconnect our spines, because we want to maintain connectivity between endpoints behind top of rack switch number 1 and top of rack switch number 2, even if this link goes down and that link as well. If we interconnect our devices in that manner and we run spanning tree protocol, spanning tree will eventually block links. This is a video about VxLAN, so if you don't know how STP works, why it is blocking links, please search for that information for yourself. There are lots of documentation, lots of videos on YouTube, so it is there is no problem to find information about this protocol. But eventually we will choose one of the spine switches as a root, and it will be basically administrative decision. You as a network engineer will say that spine 1 will be our STP root. This guy will have all its ports in forwarding state, and all other switches they will have to choose a root port. In this case, probably spine 2 will choose this port as a root, top of rack switch number 1 will choose this port, and top of rack switch number 2 will choose this port. And the most important thing here is that these ports here and here, they will be blocked. And again, refer to STP documentation why this is happening, why STP block ports, how it prevents loops, etc, etc, etc. But the end result is as follows. This link and this link, they are blocked and they are not used for data plane traffic. Some traffic happening here, for example, BPDUs go through these ports, but no data plane. And as I mentioned earlier, this is our 10 or 40 or 100 gig links. So we paid a lot of money to establish this connectivity, but essentially these links are not utilized at all. So how do we solve this problem? We can solve this problem, utilizing technology like virtual port channel or VPC. This technology allows us to pair our devices, to pair spine 1 and pair spine 2, and these devices will appear to our top-of-rack switches as a single big switch. So top-of-rack switch number 1 and top-of-rack switch number 2, they don't know that this big guy is essentially two separate physical boxes. This is the idea behind VPC. And finally, it means that top-of-rack switch number 2, it has port channel here. Top-of-rack switch number 2 has port channel here. And we are capable of establishing active connectivity, so all our links are utilized. We solved our initial problem. But eventually, as we expand our network, we will face another problem. So here we have top-of-rack switch number 1. Here we have more switches. And finally we have top-of-rack switch number 99. And we are still able to connect top-of-rack switch 99 to our VPC pair. So here it is called spine, but remember that it is essentially VPC pair, and physically it is two separate switches. Spine number 1 and spine number 2. And when the day comes, we have our top-of-rack switch number 100, and we simply physically cannot connect it to our spine number 1 and spine number 2 because they simply do not have any more unused, free, empty ports. So it is a physical restriction of the platform. So you can't you can insert line cards and ports to your switches to infinity. So at some point of time you will face that problem. You don't have any more unused empty ports. So what we do in that case? In that case, we will place spine number 2. And basically we will use the same approach. So it is spine number 2, but it is a VPC pair. And it is really spine number 3 and spine number 4. If we're talking about physical appearance, how it looks in the real life. So here we have exactly the same story, top-of-rack switch number 100, some switches in the middle, and top-of-rack switch number 199. Here we have port channels, and we will interconnect spine number 1 and spine number 2 via so-called back-to-back VPC. Again, I will be quite brief on those topics, STP, virtual port channel, etc., because this video is focused on VxLAN. So if you don't know how VPC works, what it does, what is back-to-back VPC, please research it for yourself. Lots of information on that topic as well. Basically, it means that all our links will be forwarding. But we still may have problems. What if we run out of switches here and we need to add top of rack switch 200? We will place one more VPC pair, which will be really spine number 1, 2, 3, 4, 5 and spine number 6. But here we face spanning tree issue one more time. So when we connect switches in that manner, using that triangle, eventually one of these links will be blocked. So again, we have lots of our expensive 10, 40 or 100 gig ports, which are basically not used. And in the end, VxLAN is a solution, and we will go and finally we can start discussing VxLAN, how it works, and what is our workflow for VxLAN. In order to make VxLAN work, we need to go through the following steps. At first, we need to establish underlay connectivity. Then, we'll need to configure VxLAN tunnels, and also we need to configure VTEPs, which stands for Virtual Tunnel Endpoint. Then we will need to learn our endpoints, and when these endpoints are actually learned, we can forward traffic, leveraging Ethernet inside UDP encapsulation. So let's go through the steps using our next diagram. So what do we have here? We have host number 1 with MAC address 1 and IP 10.10.10.11/24. So it could be our bare metal server, it could be our VM, doesn't really matter. Let's pretend that it is a physical bare metal server running, I don't know, Windows, Linux, again, doesn't really matter. We have the same host on the right side, but obviously with different MAC and different IP address. So from this information we can conclude that these guys, host number 1, host number 2, they are located inside the same subnet and the same broadcast domain, so they can talk directly to each other if they need to communicate. What do we have next? Host number 1 is connected physically to VTEP number 1, and VTEP number 1, this is our top of rack switch. This is basically a fancy name for a device which will be doing VxLAN encapsulation and decapsulation. Same story here. Host number 2 is connected to VTEP 2, which is top of rack switch number 2. So this is our rack number 2, and this is our rack number 1. And a very important point here, red links, this one and this one, are regular layer 2 links, are regular classical Ethernet. So-called CE or classic or classical Ethernet. So nothing new here or nothing new here. This link works exactly the same way like our regular Ethernet switches do. So let's go further. Here we have routed links, white links. Here, here, and here, which are connected to our spines, spine number 1 and spine number 2. And again, if we're talking about particular hardware platforms, and if we are using Cisco devices, this guy could be 5K or 9K, Same story here. And those guys, they would be typically Nexus 7K or Nexus 9K. So again, as we were talking previously, these guys are top of rack switches, typically 1 rack unit in height, and these guys are big boxes, which are designed to accommodate a lot of VTEPs, so we can easily add VTEP number 3 and so on and so forth. And as I said, these links are routed links. So here we will run our so-called underlay network. The goal of this network is to establish IP connectivity between VTEPs. So each VTEP will have a loopback interface. For example, with address 1.1.1.1/32, and this guy as well will have loopback 1.1.1.2/32. And here, if we go back to our previous slide, not so far, we need to establish underlay connectivity. And what it really means that we need to establish IP connectivity between these addresses, because these addresses will act as a tunnel source for our VxLAN tunnels. If you are familiar with DMVPN and especially GRE tunnels, this works exactly the same way. So we have our tunnel interface, tunnel 0, and the key point here is that tunnel interface has some kind of source interface. It could be a physical one, for example this link, or it could be a logical one, and typically we use a logical one, and especially loopbacks for high availability, because if we bind our tunnel interface to this link and this link goes down, basically our tunnel interface also goes down, but this interface, it is still live, it is still active. So in order to utilize it, we need some kind of virtual entity. And in that case, we use loopback. In order to establish connectivity between these loopbacks, we will use routing. It could be OSPF, it could be ISIS, it could be EIGRP, it could be RIP, it could be static routes. It doesn't really matter. What matters is connectivity between these loopbacks. And basically the only thing we care about is IP connectivity or simple ping test between these loopbacks. In most cases is enough to say that these guys are capable to establish VxLAN tunnels between them. I said that you can use static routes, you can use RIP, but in practice, of course, you will use some kind of routing protocol, because it allows you to establish connectivity dynamically. It allows you to use protocols like BFD for very, very, very fast reconvergence. So I guess, and you understand my point here. So here we establish our underlay network, and over this underlay we will build overlay network to actually forward traffic from host 1 to host 2. As you may remember, this traffic will be encapsulated inside VxLAN, not this traffic from this guy to that guy will be encapsulated inside VxLAN, inside UDP, inside IP, and inside Ethernet. And we will get back to it a bit later, what exactly happens to our headers. Now let's discuss this level, which where our spines are located. Typically, these guys, they are not aware of VxLAN, so they do not act as VTEPs. The core role, the core idea behind these devices is to just forward IP traffic. So if we go back to that encapsulation, VxLAN is encapsulated inside UDP, and UDP is encapsulated inside IP, and this is what these guys will actually be seeing, and they will make their routing decisions based on IP header. So very important point here, functionality wise or functional wise, this device here, VTEP, is very different from spine. There are some I would say tricky designs when you can also use spines as VTEPs, but since it is VxLAN 101, it is pretty basic video on VxLAN. We will not discuss such design approaches, such use cases. From a very basic standpoint, again, we have a clear separation between our physical devices. This guy is VTEP, this guy is VTEP. Again, they do encap and decap of VxLAN, encapsulation and decapsulation. And these guys, they just forward IP traffic. So we established underlay connectivity. Now we need to configure VxLAN tunnels or virtual tunnel endpoint VTEPs. I don't have much information to say about that configuration at this point, and most of that information actually I've already said. We need to define loopback address. We need to tie that loopback address to our tunnel interface, which will be called NVE interface. Let me quickly check this step. Yes, it is called NVE from configuration standpoint. So we tie our NVE interface to our loopback here and loopback here. And again, as I said, it is very similar to GRE. But instead of GRE, we have NVE. So we basically can use those terms interchangeably. So we can replace GRE with NVE. Meaning and the core idea is basically the same. GRE is tunnel interface, NVE is also a tunnel interface. Next we have learning endpoints, but right now we won't focus on that process. We will get back to that step in the next slides, because there is some type of control plane involved. We will assume that VTEP1 knows about host number 2 and VTEP2 knows about host number 1. And one more thing, one more assumption at this point. This guy here, I actually don't remember what I told you. Is it Windows or is it Linux? Doesn't matter. Let's say that it is Windows 1. And this is Windows 2. And our next assumption is that these guys somehow populated ARP cache. So when Windows number 1 wants to talk to 10.10.10.12, it knows this MAC address. It is populated inside its ARP table or ARP cache. So we can go back and discuss our final step, forward traffic leveraging Ethernet inside UDP encapsulation. So what happens here? Let me clear some things here. And let's go step by step. So this guy wants to communicate, and let's assume that Windows number 1, Windows on the left side of the screen, initiates connection. It knows about it knows in its ARP cache that IP 10.10.10.12 has MAC address 002. So it is capable to construct layer 2 Ethernet frame. And it actually does so. So it will create, let's assume that it is ICMP ping, which will be encapsulated inside. So basically this guy here pings this guy here. So it is ICMP, which is encapsulated inside IP. IP is encapsulated inside Ethernet. And here inside IP we have source of that host and destination of this host. Same story with Ethernet. We have source MAC address 01 and destination MAC address 02. And this frame goes to the VTEP. So first step is done. Host 1 generated Ethernet frame and forward it to its VTEP or top of rack switch. What VTEP number 1 does? Again, remember that we have that assumption that it somehow knows about host number 2. And what actually VTEP number 1 has in terms of tables, in terms of what exactly VTEP number 1 knows about host 2. It knows its MAC address, it knows its IP address, .12, and what is most important, it knows that this host belongs to VTEP number 2. So it resides below VTEP number 2. Again, this guy has loopback 1.1.1.2, if I'm not mistaken. And basically, this point, this entry in that cache at VTEP number 1, it says that host number 2 is located at VTEP number 2 behind IP address .1.1.1.2. So basically, VTEP number 1 knows that in order to reach host number 2, it needs to encapsulate that original frame, which it received from host number 1, it needs to encapsulate it inside VxLAN, inside UDP, put IP header, and in that IP header, destination IP would be 1.1.1.2, and source IP would be 1.1.1.1. So let me put it completely. So we have our ICMP, then we have IP, then we have Ethernet. This is our original frame from host number 1. VTEP number 1 receives that frame. It understands that based on Ethernet header, it understands that it should forward it to VTEP number 2 with IP 1.1.1.2. So it encapsulates it inside VxLAN. VxLAN is encapsulated inside UDP. UDP is encapsulated inside IP. And here we will construct one more Ethernet frame. And again, let me point it one more time. IP source here. Source IP is equal to loopback of VTEP 1 and is equal to 1.1.1.1. And destination IP is equal to this loopback and this information goes into IP header. And finally, this frame is ready to be sent towards spines. And here, actually, that ECMP, that load balancing, may happen. Let's talk about it a little bit. What exactly happens? VxLAN header, we won't talk about it right now. We will talk about UDP. Destination UDP port for VxLAN always would be the same. I don't remember exact ports. It could be 4879. Actually, don't believe me. Just Google VxLAN port number. Like many TCP/IP applications, it is standardized ports, and these guys, VTEP number 1, VTEP number 2, they are listening for that for traffic on that VxLAN port number. So UDP destination port always will be the same. What changes is UDP source port. And it will be changing per flow. So again, this header is for ping between host 1 and host number 2. Let's assume that besides ping we also have, I don't know, web browsing. So host number 1 is web client and host number 2 is web server. It would be TCP port 80 instead of ICMP. It would be different flow. So VTEP 1 would be able to change UDP source port. So for our first flow, which is ICMP, UDP source port would be, for example, 1000, and for web, UDP source port would be 2000. And based on that 5-tuple algorithm, VTEP number 1 would be able to send flow number 1 to spine 1 and flow number 2 to spine 2. This is basically algorithm behind VxLAN load balancing. So we went through step number 1. What happens between host and VTEP? VTEP has done encapsulation, VxLAN encapsulation, and it sent int frame towards spine 1. Now spine 1 receives that frame, and as I said before, spines just do IP routing. So again, let's quickly draw that frame. ICMP, IP, Ethernet, VxLAN, UDP, IP, and one more Ethernet. Ethernet on this link. So this would be Ethernet source MAC address would be this guy, and Ethernet destination would be that guy. So spine number 1 receives that frame, and it make its forwarding decision based on IP address inside IP header. As I told you before, here is our underlay network. And not only VTEP 1 knows about VTEP 2 loopback address. Spine 1 knows about this loopback address, spine number 2 knows about this loopback address. So there is no problem for spine 1 to forward traffic with that IP header. Again, destination IP in that header is 1.1.1.2 and source IP is 1.1.1.1.1, but from forwarding point of view, it doesn't really matter. Routers, they forward based on IP destination, if we're talking about vanilla routing. So it looks inside this IP header, makes its routing decision, and basically it means that it forwards traffic to VTEP number 2. Of course, Ethernet header, outer Ethernet header would be rewritten to represent these MAC addresses, but eventually VTEP 2 receives again that frame. VTEP 2 unpacks it. It sees that IP destination is equals to himself or itself, because IP destination there is 1.1.1.2. VTEP 2 owns that IP address, so this IP address is destined to him. Then it looks inside UDP. Again, inside UDP, UDP destination port is VxLAN. UDP destination port is VxLAN, which is well-known port. Because VTEP 2 is a VTEP, it listens for that port, it understands that it should decapsulate that and work on with that frame. It somehow needs to forward it to the next point. So we are done with IP header, we are done with UDP header. Next we have VxLAN header. At this moment, you should really care about one thing inside VxLAN header. There is 24-bit VNI, virtual network identifier. For now, you can safely correlate it or compare it with VLAN ID. So in the same manner as we have VLAN 10, VLAN 20, VLAN 100, we would have VNIs. So basically, VNI is identifier for inside VxLAN networks, and in regular networks, that identifier is VLAN ID. Based on that VNI identifier, VTEP number 2 understands which table it should look at, because in the same manner as we have VLANs, in the same manner as we have different VLANs in regular networks, we may have different VNIs, so VTEP number 2 should understand which CAM table it should look at. Based on that VNI number, it understands it, and now it has its original. It had that original Ethernet frame which host 2 originated. And based on its local classical Ethernet CAM table, it is capable to forward it to host number 2. Because, again, these links are classical regular Ethernet. So this is very, very basic overview of VxLAN workflow and VxLAN data plane. Okay, let's go through all the steps one more time to clarify it for sure. So host number 2 wants to ping host number 1, wants to ping host number 2. It has its MAC address and IP address inside its ARP cache, so it is capable to talk to it directly and form Ethernet frame. This frame is formed and sent to VTEP. This is step number 1. Step number 2. VTEP looks at that frame, and based on its table, on its database, it knows that host with this MAC address, which is inside that frame which it just received, it knows that that MAC address resides below VTEP number 2. And in reality, it knows that for that layer 2 traffic for MAC address 002, it should encapsulate inside VxLAN and forward to 1.1.1.2. And 1.1.1.2 is loopback of this guy. Then it sends it to spine number 1, and again, depending on eSIMP, depending on load balancing, it could be spine number 2. Spine number 1 is a regular IP router. It just looks at IP header, and based on that, and based on destination IP in that IP header, it forwards the traffic to VTEP number 2. VTEP number 2 receives that frame. It sees that IP destination is equals to himself. It sees that UDP port is a VxLAN well-known UDP port. So it decapsulates it, it decapsulates IP, decapsulates UDP. It looks at VxLAN header. There is VNI located. He looks at VNI ID and understands which CAM table it should look at. Then he looks at that CAM table, and it knows that it should forward the traffic to host number 2. So basically, somewhere in its CAM table, it knows that MAC address 002 is located behind, I don't know, port Ethernet 1/10. Let's assume that this is Ethernet 1/10. This traffic is received by host number 2, and for host number 2, it is just a regular Ethernet frame. So eventually, and in the end, host number 1 and host number 2, they don't know anything about VTEPs, spines, routed links. They don't know anything about VxLAN, VNIs, VTEPs, etc., etc., etc. For them, it's just a regular Ethernet, and it looks like these guys are connected to a regular layer 2 switch. I don't know, Catalyst 2960, 3750, Nexus 5K. and so on and so forth. So this concludes basic workflow and data plane for VxLAN. And now we need to go back and talk about control plane. In the last example, I made two pretty significant assumptions. I said that host 1 has ARP cache and it knows MAC to IP mapping for host number 2. And I said that VTEP number 1 somehow knows that host number 2 is located behind VTEP number 2. Now let's actually investigate, let's explore how this information is populated. But let's start with endpoint learning in regular Ethernet. So let's assume that we have host number 1, which is connected to switch 1. Switch 1 is connected to switch number 2, and switch number 2 is connected to host number 2. So here we have port number Ethernet 1/1. This port is Ethernet 1/20. This port on switch 2 is Ethernet 1/30, and this is Ethernet 1/3. So, of course, and now I'm going to talk how switch number 1 and switch number 2 are going to build their CAM tables. Of course, it depends on your state of the network. Are we going about initial endpoint learning, or are we talking about situation when our network is somewhere in the middle, when endpoints are already known? But anyways, when let's assume that host 1 is just jumped on the network, it sends some frame, and via receiving that frame, upon receiving that frame, switch 1 knows that host 1 is located behind interface Ethernet 1/1. It sends that frame over trunk link between switch 1 and switch number 2, and this is how switch number 2 knows that host number 1 is located behind Ethernet 1/30. And let's assume that host number 2, it has been on the network for a while. So switch number 2 knows where host number 2 is located, and it is located behind Ethernet 1/3. So traffic goes like that. Host number 2 receives it. It sends replies. Switch number 2, because it already knows about host number 1, it sends its out interface Ethernet 1/30. Now switch number 1 learns about host number 2. It is located behind Ethernet 1/20, and it is capable to forward it to host number 1. So this is how vanilla Ethernet works. I'm sure you are familiar with that. So what happens with VxLAN? We also have similar option. So for endpoint learning, we have flood and learn mechanism. Also we have BGP EVPN, but at first let's discuss flood and learn. So let's assume that host number 1 doesn't know anything about host number 2 except for its IP address. So it needs to send ARP request. And as you know, ARP request is a broadcast frame, so it has all Fs as MAC destination. It sends it to VTEP number 1, and again, our previous assumption doesn't work. VTEP doesn't know about host number 2. So now VTEP receives that frame and it sees that it is broadcast. And now we need to go to our next bullet, which is BUM handling. BUM is broadcast, unknown unicast, and multicast. Our VTEP number 1, it received broadcast frame, so it needs to leverage BUM handling mechanism. There are two BUM handling mechanisms, multicast and hand replication. Let's start with multicast. If we are leveraging multicast, it means that VTEP number 1 VTEP number 2 and all VTEPs that we have, they will be multicast forwarders and multicast receivers. So they will choose multicast group. Actually, we'll configure it. For example, 239.0.0.10. And let's assume that we will use that group for VNI number 10, and we use VNI number 10 for our host number 2 and host number 1. So VNI number 10, it is using multicast group 239.0.0.10. Multicast group VTEP number 1 receives broadcast frame on that VNI, on VNI 10. It is configured with multicast. VNI number 10 is configured with this specific multicast group, and it means that the traffic, that ARP request should be forwarded using that multicast group. So again, VTEP number 1 is multicast sender and both multicast receiver for that group. The same story for VTEP 2, and these guys in the middle, they also need to participate in multicast routing. Actual implementation may vary, because 5K platform uses BIDR for multicast. With VxLAN 9K platform, they are capable to use regular PIM sparse mode. Again, we will not dive into those details in this video. The point here is that we have underlay network. We already talked that it has either IS-IS or OSPF for unicast routing, and the same story for multicast. We need some kind of protocol enabled, for example, PIM sparse mode, in order to forward traffic for that multicast group. So spine, actually here for now we can replace it with spine. RA stands for router reflector, and we will talk about it a bit later. It receives traffic for that multicast group according to multicast control plane and data plane. It will forward that traffic, and eventually VTEP number 2 will receive that ARP requests. And here two interesting things happen. So it receives that ARP request. It decapsulates that ARP request essentially from VxLAN, and because we have source MAC address inside this ARP request, and it was encapsulated inside VxLAN with loopback address of VTEP 1, VTEP number 2 now knows that this MAC address 0001 is located behind VTEP number 2. So it is capable to populate its table. It knows that MAC address 001 is located behind VTEP number 1, and essentially VTEP number 1 has IP address 111.1.1.1. This is first thing, and the next thing is that ARP request is decapsulated and forwarded to host number 2. Host number 2 receives it as a regular ARP requests. It sends ARP reply. Again, ARP reply is unicast, and it is unicast with MAC address in its destination set to this MAC address 0001. VTEP number 2 already knows about it, so it is capable to send ARP request or ARP reply, directly to VTEP number 1. On that stage, so let's quickly recap. Here is step number 1. Here is step number 2. So this is regular Ethernet. This is ARP request encapsulated inside multicast. Here is VTEP number 2 receives it, decapsulates it, sends it to host number 2, and on step 4 we receive ARP. We send ARP reply, which is unicast. On step number 5 VTEP number 1 receives ARP reply and is capable to do the same thing. Now it knows that MAC address 0002 is located behind VTEP 2 and essentially behind IP address 1.1.1.2. Because again, ARP reply is Ethernet unicast frame with source MAC address 0002, destination MAC address 0001, so VTEP 1 is capable of populating that entry in that table. So essentially at that point, VTEP number 1, it knows that 0001 is local, and 0002 is behind VTEP number 2. And VTEP 2 knows that 0001 is behind VTEP number 1, and 0002 is local. It is behind this port. And at that point of time, host number 2 is capable to talk to host number 1 is capable to talk to host number 2, and this traffic will be just regular unicast, assuming that these guys are talking using unicast. So if it's ping, it will be just regular unicast traffic, so no multicast from that point. So multicast was used only to make that initial ARP resolution. So now we discussed endpoint learning with flood and learn mechanism. We discussed how broadcast and non-unicast and multicast handling is handled with multicast. Now we need to talk about head and replication. This is pretty simple. Instead of multicast, we can use basically replication. It means that VTEP number 1, it has some kind of table, and in that table it has all required information about all VTEPs. So it knows about VTEP number 2, and it knows its IP address. It knows about VTEP number 3, and it knows about its IP address as well. And so on and so forth. It knows about VTEP number 99 with IP address 111.199. How this table is populated is out of scope for this video. It already would be a pretty long one. But basically it could be either statically configured or derived from some protocol, so from some protocol exchange. Anyways, VTEP number 1 knows about all other VTEPs, and for example VTEP number 2 also knows about all the other VTEPs. So every VTEP in your VxLAN network knows about all other VTEPs in your network. So instead of leveraging multicast, VTEP number 1 will just create 99 replicas of that ARP request. Or in our case, it will actually make just a single one, because we have only 2 VTEPs. But again, if we had 99 VTEPs, it would create 98 replicas. 98 because again, if we here have VTEP number 99 and we have all other VTEPs in the middle, VTEP number 1 needs to create replicas for all other VTEPs. So if we have 99, we will subtract ourselves and we will get 98 replicas. So it will send those 98 replicas as IP unicast. So these guys will receive that. So problem solved. But obviously it has some scalability issues, because if we utilize multicast, we send just a single frame, and our multicast core, our multicast network will replicate it. If we use head-on replication, each VTEP will be responsible for creating all those replicas. So obviously, if you have lots of VTEPs and if you have lots of BUM traffic, you will pretty soon hit that scalability limit. So we talk about again endpoint learning with flood and learn, and how we can handle BUM traffic with multicast and hand-on replication. But I'm sure I will talk about it a bit later. BUM handling applicable not only to flood and learn, it also will be applicable to BGP EVPN. And now let's talk about BGP EVPN. If we utilize BGP, we would basically be able to offload all information that we have locally about IP addresses of directly connected endpoints, MAC addresses of directly connected endpoints to BGP table and distribute it across the whole fabric. So in our particular case, as soon, let's go step by step. In our particular case, VTEP number 1 would run BGP process. VTEP number 2 also would run BGP process. And these guys, our spines, they will be route reflectors. So they also would be will be running BGP process, but again, they won't be doing VxLAN encapsulation or decapsulation. So from BGP standpoint and from EVPN standpoint, they are only BGP routers. So the whole idea behind those guys is to exchange routing information. So in case with regular BGP, it's IP prefixes. In case with EVPN, BGP EVPN, it would be MAC addresses, IP addresses, and also prefixes. So all these guys run some kind of BGP. When VTEP number 1 learns about host number 1, so for example, if we just plug in our computer to the network, chances are that 99% of systems, they will send at least some initial traffic, some ARP requests for its default gateway. They will talk, I don't know, some systems in the cloud, doesn't really matter. The point here, when you plug your system inside the network, it generates some traffic. Of course, there are 1% of systems which don't do that. They are also called silent hosts. We will talk about it, I believe, in other videos, not in this one. This is getting really long. So 99% will generate some traffic. This traffic will reach VTEP number 1. So VTEP number 1 knows that MAC address 001 is local, and it will redistribute this information into BGP. So we have our CAM table, which says that 0001 is located behind Ethernet 1/1. After that, we redistribute that information to BGP, and this information about that MAC address, it becomes a route, some kind of route. But instead of physical port, it will contain VTEP number 1 loopback. This BGP route will be propagated to route reflectors, and as you may know how route reflectors work, they will reflect that route to VTEP number 2. So eventually, in the very end, VTEP number 2 knows that MAC address 0001 is located behind VTEP 1, with IP address 1.1.1.1. Exactly the same story happens in the opposite direction. So basically, as soon as you plug your hosts to your network, this information goes into CAM table. CAM table is redistributed inside BGP. BGP routes is exchanged, so everyone in your network, every VTEP in your network knows about all MAC addresses and where they are actually located. So we don't need to flood traffic in order to learn them. We have all that information inside BGP EVPN table. And scalability limit is not an issue in that case because, as you may know, I believe nowadays BGP IPv4 full view is around 700,000 routes. So if you receive one full view from your ISP. So obviously new platforms like Nexus 9K, they are capable to cope with those numbers of MAC addresses. And the key point here, actually, sorry, let me go back that. The very key point here is that VTEP number one, it has information about all endpoints in the fabric. It could be hundreds of thousands MAC addresses, but it will install in the hardware, in the TCAM, only those information which it really needs. But again, it is a bit out of scope for our for this video. So I believe more or less we covered those topics. So we talked about how endpoint could be learned. Again, we could either leverage flood and learn, but in reality you will use BGP EVPN. And for BUM handling, we will use either multicast or head-end replication. Again, multicast is better, but of course, if you want to use leverage, if you want to use multicast, your underlay network must support multicast. That's pretty obvious. But if your fabric is quite small, head-end replication is a possible solution, I would say. So we are ready to talk about our final topic for today, which is routing with VxLAN. So far we were talking about just regular bridging, how VxLAN networks forward traffic, assuming that hosts are in the same IP subnet and the same broadcast domain. Now we need to talk about routing, which means that we are going to talk about situations when host number one is in VNI and subnet 1, and host number 2 is VNI number 2 and subnet number 2, so broadcast domains and subnets are basically different. There are two approaches for routing, which is called Asymmetric IRB and Symmetric IRB. IRB stands for internal or integral, I'm not sure, integrated. I believe it's integrated routing and bridging. So now we will discuss all these options, and as well we are going to talk about the concept of Anycast gateway. At first, let's discuss this concept of Anycast gateway. And we will talk about it using asymmetric IRB. So asymmetric IRB implies that traffic from source to destination uses VNI X and traffic from destination to source uses VNI Y, different VNI, and it in the end implies that all VTEPs must be configured with all VNIs and corresponding default gateways. So what it really means. So in that case we have host number 1, which is located inside VNI 110, and it has IP 10.10.10.11. And we have host number 2, which is inside VNI 120, and it has IP 10.20.20.12. So again, these hosts are in different VNIs and different IP subnets. What is Anycast gateway? It means that SVI or default gateway for those VNIs will be located at each VTEP. So in our legacy or regular networks, we have concept of FHRP, or first hop redundancy protocols, such as HSRP, VRRP, GLBP, and those protocols, they typically have some kind of limitation that either for number of active devices at the same time, or they do not support active forwarding at all. And typically we place active pair of devices or some number of active devices at some place in your network. So here we place our HSRP pair, and those devices are basically doing routing, inter-VLAN routing. But it's significantly different with VxLAN. With VxLAN, each VTEP is the default gateway for hosts below it. So, for example, if VTEP number 1 has 100 different hosts, it will be serving as default gateway for all of them. And it means that it is configured with default gateway for all those VNIs. So in our case, it is configured as 10.10.10.1, which is default gateway for this subnet. And it is configured with 10.20.20.1, which is default gateway for that subnet. And exactly the same is happening here on VTEP number 2. So if you are familiar with concept of Anycast, it means that you have basically duplicate IP addresses inside your network, but it won't cause any problem because Anycast uses the approach route to my closest gateway. So for host number 1, closest default gateway is located inside VTEP number 1. For host number 2, closest VTEP is located inside at VTEP number 2. So the key point here is that all VTEPs have default gateways for all hosts which are directly connected to them. Now let's go back to Asymmetric IRB. In this situation, in this particular setup, VTEP number 1, it has host number 1 inside VNI 110. It doesn't have hosts in VNI 120, but it still has to have that VNI and that default gateway. The opposite story here is VTEP 2. VTEP 2 has host number 2, which is inside VNI 120. It has default gateway for that VNI, but it also has to have default gateway for VNI 110. It happens because of asymmetric nature. So what happens here? Host number 1 wants to talk to host number 2. It is configured with it realizes that host number 2 is in different subnets, so it needs to go to its default gateway. Default gateway is located at VTEP number 1. VTEP number 1 receives the traffic and it makes a routing decision. So it routes traffic between VNI 110 to VNI 120, And after that, it bridges the traffic to VTEP number 2. So it does exactly the same thing which we discussed in our previous examples. So it at first routes traffic between VNIs, and then it bridges it to VTEP number 2. So in the underlay, traffic will traverse inside VNI 120, yes, correct. VTEP number 2 receives the traffic, it receives it inside VNI 120, and it bridges it to host number 2. Host number 2 receives the traffic, it sends reply, again, it sends reply to its default gateway, which is 10.20.20.1. VTEP number 2 makes opposite forwarding decision. It routes from VNI 120 to VNI 110. And after that, again, it bridges the traffic over overlay, and it uses VNI 110. Because at first it routes from that VNI to this VNI, and inside VNI 110, it bridges it to VTEP number 2. So, let me use different colors. So this is our VNI 110, and traffic from host 1 goes like that. Then it goes, reply from host 2 goes that way. Here it gets routed to VNI 110. Sorry, that's not correct. One more time. So when host 1 docks to host 2, it goes to its default gateway. Here is our VNI 120, because it goes like that. It gets routed here. It goes through that VNI, it goes to VTEP number 2, and hits host number 2. Host number 2 sends a reply. It goes to its default gateway, and now it routes from VNI 120 to VNI 110. It gets routed, and it gets breached via VNI 110. So, as you can see, this is why it is called asymmetric. In the direction from left to right, from host 1 to host 2, we at first go to default gateway 10.10.10.1. We route traffic to VNI 120. We breach over that VNI to VTEP 2. Then host 2 sends reply. In the reverse manner, it goes to default gateway 10.20.20.1. It gets routed to VNI 110, and it gets breached again that VNI. It implies that from left to right, we go through VNI 120 in the overlay, and from right to left we go through VNI 110. And as it is mentioned here, it means that all VTEPs must be configured with all VNIs and corresponding default gateways, even if they don't have those endpoints directly attached. So VTEP number 1, it doesn't have any endpoint inside VNI 120 directly connected, and VTEP number 2, it doesn't have any endpoints inside VNI 110 directly connected. So again, we hit that scalability issue. So how do we solve that? We solve that with Symmetric IRB. Traffic from source to destination uses separate layer 3 VNI. Traffic from destination to source uses the same layer 3 VNI. So we do pretty simple thing. Here we have basically the same setup, but VTEP number 1, it has VNI for its directly attached host number 1, and VTEP number 2 has VNI for its directly attached host, which is host number 2. And VTEP number 1 and VTEP number 2, they use special layer 3 VNI, which is VNI 10,000, for routed traffic. So when VTEP 1 knows that it has to route some traffic, it will go from VNI 110 to VNI 10,000, go through it VNI, VTEP number 2 receive traffic again inside this VNI, it again understands that it needs to route, it will route it to host number 2, and the reverse path will be exactly the same. They again will use that so-called layer 3 VNI. And it allows us, and it allows our VTEPs to have only VNIs for hosts that are directly attached. So VTEP number 1 has host 1 directly attached with VNI 110. That's why it has default gateway for 110 VNI. VTEP number 2, it has host number 2, which is inside VNI 120, and it has VNI for 120. So it doesn't have all other VNIs for hosts. It doesn't have as directly attached. So at this point, I want to conclude this video. So I think we discussed a lot today. So we talked about benefits of VxLAN. We talked about how industry came from regular Ethernet, STP, VPC, and other technologies to routing Ethernet traffic, to actually routing Ethernet traffic over some kind of overlay. We talked about VxLAN workflow, how it actually works, what happens to headers, how routing works with VxLAN. So I guess it's pretty good overview of what VxLAN is. So if you like this video, please put a thumbs up, subscribe to my channel, tell about this channel to your friends, to your colleagues. Again, thank you so much for your attention. See you later. Bye.